Hey, you all. Did you know that if you fell into a black hole, your body would be stretched into a long, thin strand, like spaghetti, before you even reach the center? And that's just the beginning. What happens inside a black hole challenges everything we think we know about space, time, and reality itself. In this video, we're going to take a deep dive, literally, into what it would be like to fall into a black hole. We'll explore the event horizon, the point of no return, tidal forces which can rip you apart atom by atom, and the mind-bending curvature of spacetime that makes black holes some of the most extreme objects in the universe. Whether you're listening while you sleep or wide awake, you're about to learn real physics. No fluff, no fantasy, just the science as we understand it today. So relax, get comfortable, and let's journey together toward the edge of forever. First, let's talk about what a black hole actually is. At its core, a black hole is not a hole in the usual sense. It's not an empty tunnel or a cosmic vacuum cleaner sucking in everything nearby. Instead, a black hole is an incredibly dense concentration of mass packed into a tiny region of space. When a massive star runs out of fuel, it can no longer support itself against its own gravity. The core collapses inward, and if the star is massive enough, usually more than about 3 times the mass of our sun, that collapse doesn't stop. It keeps going until all that matter is crushed into a point of infinite density called a singularity. Around that singularity lies a boundary known as the event horizon. Once anything crosses this boundary, not even light can escape. That's why it's called a black hole, because no light comes out, so we can't see it directly. Now imagine you're floating in space, far from any black hole. You feel weightless, just drifting along. But suppose you're on a mission. Maybe you volunteered, maybe you were tricked, and you're now heading straight toward a stellar mass black hole, one formed from the collapse of a single star. As you approach, strange things begin to happen. Not because the black hole is pulling you in with some mysterious force, but because the fabric of spacetime itself is warped by the black hole's immense mass. To understand this, we need to step back and talk about gravity, not as a force in the Newtonian sense, but as the curvature of spacetime, as described by Einstein's theory of general relativity. In this view, massive objects don't exert a pull on other objects. Instead, they curve the very stage on which everything plays out, space and time combined into a 4-dimensional continuum. Think of spacetime like a stretched rubber sheet. If you place a heavy ball in the center, it creates a dip. Now roll a smaller marble nearby. The marble will curve toward the heavy ball, not because it's being pulled, but because it's following the shape of the sheet. That's gravity. And near a black hole, that dip becomes infinitely steep. So as you fall toward the black hole, you're not being yanked by a rope. You're simply following the straightest possible path through curved spacetime. In physics, we call this a geodesic. It's the natural trajectory of a freely falling object. From your perspective, you feel nothing unusual at first. You're in free fall, so you're weightless, just like astronauts orbiting Earth. But someone watching you from far away would see something very different. This brings us to the event horizon. The event horizon is not a physical surface. It's an imaginary boundary in space surrounding the singularity. Its radius is called the Schwarzschild radius, named after Karl Schwarzschild, who first solved Einstein's equations for a non-rotating black hole in 1916. The formula for the Schwarzschild radius is the Schwarzschild radius equals 2 times the gravitational constant times the mass of the black hole divided by the speed of light squared. Written out fully, R sub s equals 2 times g times m divided by c squared. Let's plug in some numbers to make this concrete. For a black hole with the mass of our sun, which is about 2 times 10 to the 30th kilograms, the Schwarzschild radius is roughly 3 kilometers. That means if you could somehow compress the entire sun into a sphere less than 6 kilometers across, it would become a black hole. For Earth, the Schwarzschild radius is only about 9 millimeters. So yes, in theory, you could turn Earth into a black hole, but you'd need unimaginable pressure to squeeze it that small. Now back to your fall. As you get closer to the event horizon, time itself begins to behave strangely. According to general relativity, gravity affects the flow of time. The stronger the gravitational field, the slower time passes relative to a distant observer. This is called gravitational time dilation. So from the perspective of someone watching you from a safe distance, your clock appears to tick slower and slower as you approach the event horizon. In fact, they would never actually see you cross it. To them, you seem to freeze just outside, fading from view as your light gets redshifted into invisibility. But from your own perspective, inside the falling spaceship, you experience something completely different. Your watch ticks normally. You don't feel any sudden jolt or barrier as you cross the event horizon. If the black hole is large enough, like a supermassive black hole at the center of a galaxy, you might not even notice anything unusual at the moment of crossing. There's no flashing sign that says, "You are now inside a black hole." The event horizon is locally undetectable. It's only when you try to send a signal back out that you realize you're trapped. Any light beam you shine outward bends back toward the singularity. Space itself is falling inward faster than light can move against it. This leads to a profound insight. Inside the event horizon, the roles of space and time switch. Outside the horizon, you can move freely in space but are forced to move forward in time. Inside, however, all future-directed paths lead inexorably toward the singularity. Time, in a sense, points toward the center. No matter how powerful your rockets are, you cannot stop or reverse your motion. You are doomed to hit the singularity, not because you're being pulled, but because that's the only direction the future goes. But before you reach the singularity, you'll likely be torn apart by tidal forces. Tidal forces arise because gravity isn't uniform. It gets stronger the closer you are to the source. Imagine standing upright near a black hole. Your feet are closer to the singularity than your head, so they feel a stronger gravitational pull. This difference in gravitational strength across your body creates a stretching force. At the same time, gravity pulls your sides inward toward the center line of your body, compressing you horizontally. The result, you're stretched lengthwise and squeezed sideways, a process physicists grimly call spaghettification. The strength of these tidal forces depends on the size of the black hole. For a small, stellar mass black hole, say 10 times the mass of the Sun, the event horizon is only about 30 kilometers across. The gradient of gravity over just a few meters is enormous. You'd be spaghettified well before you even reached the event horizon. But for a supermassive black hole, like the one at the center of our Milky Way, which has a mass of about 4 million suns, the event horizon is millions of kilometers wide. The gravitational gradient at the horizon is much gentler. You could cross the event horizon intact, only to be shredded later as you got closer to the central singularity. We can calculate the tidal acceleration using Newtonian gravity as a good approximation, even though we're dealing with strong fields. The formula for the tidal acceleration across a distance L is tidal acceleration equals 2 times the gravitational constant times the mass of the black hole times the length L divided by the distance from the center cubed. Written out, a tidal equals 2 times g times m times L divided by r cubed. Let's say you're 2 meters tall, so L equals 2 meters, and you're approaching a 10 solar mass black hole. At a distance of 100 kilometers from the singularity, the tidal acceleration across your body would be on the order of billions of meters per second squared. That's enough to rip apart atoms. But if you're falling into a supermassive black hole with a mass of 1 million suns, the same tidal force at the event horizon might be less than 1 meter per second squared, barely noticeable. This is why, paradoxically, bigger black holes are safer to fall into, at least initially. Their immense size smooths out the curvature of spacetime near the horizon, making the ride less violent. But safety is relative. Once inside, your fate is sealed. Now let's talk more deeply about spacetime curvature. In general relativity, the presence of mass and energy tells spacetime how to curve, and the curvature of spacetime tells matter how to move. This relationship is encoded in Einstein's field equations, which are among the most complex and beautiful equations in physics. While we won't write out the full tensor form here, the essence is this. The geometry of spacetime is directly linked to the distribution of mass and energy within it. Near a black hole, spacetime is so severely curved that light cones, the boundaries that define what events can influence each other, tilt inward. Outside the event horizon, your future light cone still points mostly forward in time, with some room to move in space. But inside, the entire light cone points toward the singularity. Every possible future leads to destruction. There are no paths that loop back, no escape routes, not even for information. This raises deep questions about the nature of reality. What happens to the information that falls into a black hole? Does it vanish forever, violating quantum mechanics? This is the famous black hole information paradox, a puzzle that has occupied physicists for decades. Some theories suggest information is encoded on the event horizon itself, like a hologram. Others propose that black holes eventually evaporate via Hawking radiation, releasing their contents back into the universe. But whether that preserves information is still debated. But let's return to your personal journey. Suppose you've crossed the event horizon of a supermassive black hole. You're still alive, still conscious. The lights in your ship are on. You look out the window. What do you see? Surprisingly, the view isn't completely dark. Light from the outside universe can still fall in after you, so you'd see the entire future history of the cosmos speed up in a flash of blue-shifted light, but only for a brief moment. Because once inside, you're falling so fast that even incoming light struggles to catch up. The sky behind you would appear as a shrinking circle of light, getting bluer and brighter, then vanishing as you plunge deeper. Ahead of you toward the singularity, it's pure darkness, but not empty darkness. Space is so distorted that directions lose meaning. Down is no longer a spatial direction, it's your future, and that future is short. For a stellar mass black hole, the trip from horizon to singularity might take microseconds. For a supermassive one, it could be hours. But inevitably, you reach the end. What is the singularity? In classical general relativity, it's a point where density becomes infinite, spacetime curvature becomes infinite, and the laws of physics break down. It's not a place in space, it's a moment in time, the end of your timeline. But physicists believe that general relativity alone can't describe the singularity. At such extreme scales, quantum effects must become important. We don't yet have a complete theory of quantum gravity, but candidates like string theory and loop quantum gravity suggest that the singularity might be replaced by something else, a bounce, a wormhole, or a new universe. But these are speculations. For now, the singularity remains the ultimate unknown. Now let's clarify a common misconception. Black holes don't suck things in like cosmic vacuum cleaners. Far away from a black hole, its gravity behaves just like any other massive object. If you replaced our sun with a black hole of the same mass, Earth would continue orbiting exactly as it does now, just in the dark. You only get into trouble when you get very close, where the extreme curvature dominates. Another point, rotating black holes described by the Kerr solution are more realistic than the simple Schwarzschild black holes we've been discussing. Most stars spin, so when they collapse, the resulting black hole also spins. Rotation changes the structure dramatically. Instead of a point singularity, you get a ring singularity, and around it lies a region called the ergosphere, where spacetime itself is dragged around by the black hole's rotation. In theory, you could extract energy from this region, a process called the Penrose mechanism. But even in a rotating black hole, once you cross the inner event horizon, your fate is still sealed. Let's also address time again because it's so counterintuitive. From your perspective, falling in takes a finite amount of time, but to a distant observer, you never cross the horizon. This isn't an illusion, it's a consequence of how space-time is structured. Both perspectives are valid within their own reference frames. There's no universal now in relativity. Time is relative, so who's right? Both are. Physics allows for multiple, equally valid descriptions of the same event, depending on the observer's state of motion and location in the gravitational field. This leads to another fascinating idea, the firewall paradox. Some interpretations of quantum mechanics suggest that the event horizon might not be smooth after all. Instead, it could be a seething wall of high-energy particles, a firewall that would incinerate you instantly upon crossing. This arises from attempts to reconcile general relativity with quantum entanglement near the horizon, but this is still highly controversial. Most physicists hope that a full theory of quantum gravity will resolve this without violating the equivalence principle, which says that free fall should feel like empty space. Now, let's go back to tidal forces and do a more detailed calculation. Suppose you're falling feet first toward a black hole of mass m. The gravitational acceleration at your feet is given by Newton's law. Acceleration at feet equals gravitational constant times mass divided by distance to feet squared. Similarly, acceleration at your head equals gravitational constant times mass divided by distance to head squared. Since your head is farther away, this acceleration is slightly less. The difference between these two accelerations is the tidal acceleration stretching you apart. If your height is h and your distance from the center is r, then the distance to your feet is approximately r minus h over 2, and to your head is r plus h over 2. Using calculus or a Taylor expansion, we find that the tidal acceleration is approximately 2 times g times m times h divided by r cubed. That's the formula we mentioned earlier. Now let's compare this to the acceleration due to gravity itself, which is g times m divided by r squared. The ratio of tidal acceleration to gravitational acceleration is roughly 2 times h divided by r, so the tidal force becomes significant when your height is comparable to your distance from the center, which only happens very close to small black holes. For large black holes, r is huge, so the ratio is tiny. This is why astronauts orbiting Earth don't get spaghettified. Earth's gravity is weak, and the tidal forces across a human body are negligible. But near a neutron star or black hole, the story changes. Let's also consider the experience of light. As you fall, any light you emit gets redshifted. Redshift means the wavelength of light gets stretched, shifting it toward the red end of the spectrum, and eventually beyond visible light into infrared, microwaves, and radio waves. The formula for gravitational redshift is observed frequency equals emitted frequency times the square root of 1 minus Schwarzschild radius divided by distance. So as your distance approaches the Schwarzschild radius, the square root term goes to 0, and the observed frequency drops to 0. To a distant observer, your light dims and reddens until it disappears. But again, from your perspective, nothing strange happens to your own light. Your flashlight still works normally. It's only when comparing clocks and signals across different gravitational potentials that these effects appear. Now, imagine you're not falling alone. Suppose you have a friend hovering just outside the event horizon, using powerful rockets to stay in place. To maintain that position, they must accelerate outward constantly to counteract gravity. The required acceleration becomes infinite at the event horizon, which is why no material object can hover exactly at the horizon. But if they're close, they'd see you fall in quickly, while you'd see their clock speed up dramatically due to the intense gravitational time dilation. This asymmetry is one of the most mind-bending aspects of black holes. It shows that space and time aren't fixed backgrounds. They're dynamic, responsive, and deeply personal. Let's also talk about orbits. Outside the event horizon, there are stable and unstable orbits. For a Schwarzschild black hole, the innermost stable circular orbit is at 3 times the Schwarzschild radius. Closer than that, and any object will spiral in unless it fires its engines. Photons, particles of light, can orbit at exactly 1.5 times the Schwarzschild radius in what's called the photon sphere. But this orbit is unstable. The slightest perturbation sends the photon either escaping to infinity or plunging into the black hole. If you were to skim the photon sphere, you might see the back of your own head, because light could loop around the black hole and enter your eyes. The visual distortions near a black hole are extreme, thanks to gravitational lensing, the bending of light by gravity. This effect has been observed in real astronomical images, like the famous picture of the black hole in M87 taken by the Event Horizon Telescope. But again, all of this is outside the horizon. Once you cross it, no light can orbit, no signals can escape, and no force in the universe can save you. Now let's consider energy. As you fall, you gain kinetic energy. In Newtonian physics, your speed increases as you fall toward a massive object. Near a black hole, relativistic effects dominate. Your speed as measured by a local observer approaches the speed of light as you near the singularity. But speed is tricky in general relativity because there's no universal reference frame. What matters is your proper time, the time measured by your own clock and your trajectory through spacetime. The total energy of a particle falling into a black hole is conserved in a certain sense, but defining energy in curved spacetime is subtle. For stationary black holes, there is a conserved quantity related to time translation symmetry, but inside the horizon, that symmetry breaks down. Another key concept is the no-hair theorem. It states that black holes can be completely described by just 3 properties: mass, electric charge, and angular momentum. All other details about the matter that formed them, what kind of star it was, whether it was made of iron or hydrogen, whether it had planets, are lost. The black hole has no hair, meaning no distinguishing features. This simplicity is both elegant and troubling because it suggests information is destroyed. But quantum mechanics says information can't be destroyed. So we're back to the information paradox. One proposed solution is the holographic principle, which suggests that all the information inside a volume of space can be encoded on its boundary. For a black hole, that boundary is the event horizon. So maybe when you fall in, your information isn't lost. It's smeared across the horizon in a scrambled, 2-dimensional form. Then, as the black hole evaporates via Hawking radiation over billions of years, that information slowly leaks out. Hawking radiation itself is a quantum effect. In empty space, virtual particle pairs constantly pop in and out of existence. Near the event horizon, one particle might fall in while the other escapes, making the black hole appear to emit radiation. This causes the black hole to lose mass over time. For stellar mass black holes, this process is incredibly slow, far longer than the age of the universe. But for tiny black holes, it could be explosive. However, Hawking radiation is irrelevant to someone falling in. It's far too weak to notice. Your demise will come from tidal forces or the singularity long before evaporation matters. Let's now reflect on what this journey teaches us about physics. Black holes are laboratories for extreme gravity. They test the limits of general relativity and force us to confront the need for quantum gravity. They show us that space and time are not absolute but flexible, interconnected, and observer-dependent. They remind us that the universe is far stranger than our everyday intuition suggests. And yet, despite their fearsome reputation, black holes are also creative. They power quasars, shape galaxies, and may even seed the formation of stars. They're not just destroyers, they're part of the cosmic cycle. So to summarize where we are so far, if you fall into a black hole, your experience depends critically on its size. For small black holes, you're torn apart before reaching the horizon. For large ones, you cross the horizon unharmed, only to be destroyed later by ever-increasing tidal forces as you approach the singularity. From your perspective, the fall takes a finite time. From an outsider's view, you never quite make it in. Spacetime is so curved inside the horizon that all paths lead to the center. The singularity is where our current laws of physics fail, and what lies beyond, if anything, is unknown. In the next part of this journey, we'll explore what might happen at the singularity, delve deeper into rotating black holes, examine the role of quantum mechanics, and consider whether black holes could be gateways to other universes. But for now, let this sink in. Falling into a black hole isn't just a dramatic end. It's a profound encounter with the deepest laws of nature. As you drift closer to that point of no return, remember, you're not just a victim of gravity. You're tracing the contours of spacetime itself, riding the geometry of the universe toward its most enigmatic frontier. And in doing so, you're participating in one of the greatest thought experiments in physics, one that continues to challenge, inspire, and humble us all. Now that you've crossed the event horizon, assuming you're falling into a supermassive black hole and are still intact, let's explore what happens next. The journey inward is brief but transformative, not just physically, but conceptually. Every intuition you have about space, time, and causality begins to unravel, and this is where physics gets truly strange. Inside the event horizon, the radial direction, the direction pointing toward the singularity, is no longer a spatial dimension in the way we normally think of it. Instead, it becomes time-like. What does that mean? Outside the horizon, you can choose to move left or right, up or down, forward or backward in space, but you must always move forward in time. Inside the horizon, however, moving toward the singularity is as inevitable as the passage of time itself. You cannot stop it, avoid it, or even slow it down meaningfully. Trying to fire your rockets away from the singularity would be like trying to travel backward in time outside the black hole. It's simply not allowed by the geometry of spacetime. This switch between space and time isn't just poetic language. It's a direct consequence of Einstein's equations. In the Schwarzschild metric, the mathematical description of spacetime around a non-rotating black hole, the signs of the time and radial components flip when you cross the event horizon. Before the horizon, the time component has a negative sign in the spacetime interval, and the radial component has a positive sign. After crossing, those signs reverse. This mathematical flip corresponds to a physical reality. Your future is now aligned with decreasing radius, not increasing time. So as you fall inward, you're not moving through space toward a location. You're moving through time toward an event, your encounter with the singularity. And just as you can't avoid next Tuesday, you can't avoid the singularity once you're inside. But what exactly is the singularity? In classical general relativity, it's a point where the curvature of spacetime becomes infinite. The density of matter, the tidal forces, the gravitational field, all blow up to infinity. At this point, the equations of general relativity break down. They produce nonsensical answers, like division by zero. This is a clear signal that the theory is incomplete. General relativity doesn't include quantum mechanics, and at the incredibly small scales near the singularity, where distances are smaller than an atomic nucleus, quantum effects must dominate. We don't yet have a fully accepted theory of quantum gravity, but several candidates offer different visions of what replaces the singularity. In loop quantum gravity, for example, spacetime is made of discrete, indivisible units, like pixels of space. When matter collapses to extreme densities, a repulsive quantum force might halt the collapse and cause a bounce, potentially leading to a new expanding region of spacetime, a baby universe. In string theory, the singularity might be replaced by a complex, higher-dimensional object called a fuzzball, where the information of infalling matter is preserved in intricate quantum states on the surface. But these ideas remain theoretical. For now, within the framework of known physics, the singularity represents the end of the line, not just for you, but for predictability itself. Physics loses its power to tell us what happens next. Let's return to your experience. As you fall deeper, the tidal forces grow stronger. Remember the formula. Tidal acceleration equals 2 times the gravitational constant times the mass of the black hole times your height divided by your distance from the center cubed. As your distance r decreases, r cubed shrinks rapidly, so the tidal acceleration skyrockets, even in a supermassive black hole where you cross the horizon unharmed. This force will eventually become overwhelming. First, your body stretches. Your feet accelerate faster than your head, pulling you apart. Simultaneously, your sides are compressed inward because all paths converge toward the central axis. This combination of stretching and compressing is spaghettification in action. It doesn't just affect your body, it affects every atom, every molecule. Long before you reach the singularity, your molecular bonds are torn apart. Then your atoms are ripped apart into subatomic particles. Finally, even protons and neutrons may be shredded, though our current understanding of particle physics breaks down before we can say for sure. The exact point at which this happens depends on the black hole's mass. For a black hole with a mass of 1 million suns, tidal forces might only become lethal a few minutes after crossing the horizon. For a billion solar mass black hole, like those found at the centers of giant elliptical galaxies, you might survive for hours inside. But survival is temporary. The singularity always wins. Now let's consider rotating black holes, because most real black holes spin. Rotation changes everything. A spinning black hole is described by the Kerr metric, not the Schwarzschild metric. Instead of a point singularity, it has a ring singularity, a one-dimensional ring lying in the equatorial plane. The event horizon is also different. There are actually 2 horizons, an outer event horizon and an inner Cauchy horizon. Between these two lies a region called the ergosphere, which exists outside the outer horizon. In the ergosphere, spacetime is dragged around so violently by the black hole's rotation that nothing can remain stationary, not even light. Everything is forced to rotate with the black hole. This effect, called frame dragging, is predicted by general relativity and has been observed indirectly around Earth and neutron stars, but it becomes extreme near a Kerr black hole. The ergosphere has a remarkable property. It allows for energy extraction. In 1969, physicist Roger Penrose proposed a mechanism, now called the Penrose process, whereby an object entering the ergosphere could split into 2 parts, with one part falling into the black hole and the other escaping with more energy than the original object had. The extra energy comes from the black hole's rotational energy, effectively slowing it down. This isn't science fiction. It's a legitimate prediction of general relativity. In principle, an advanced civilization could use this to harvest vast amounts of energy from a spinning black hole. But if you fall past the outer horizon of a rotating black hole, things get even weirder. Inside, the ring singularity has bizarre properties. Unlike a point singularity, the ring has a finite size, and mathematically, you could pass through the center of the ring without hitting infinite curvature. Some solutions of the Kerr equations suggest that passing through the ring might lead to other regions of spacetime, perhaps other universes or other parts of our own. These are called maximally extended solutions, and they include wormholes and closed time-like curves, paths that loop back in time. However, most physicists believe these features are mathematical artifacts, not physical realities. The inner Cauchy horizon is likely unstable. Any infalling matter or radiation would pile up there, creating an infinite burst of energy, a phenomenon called mass inflation, that would destroy anything approaching it. So while the math allows for exotic possibilities, nature probably forbids them. Still, the idea that black holes could connect distant parts of the universe, or even different universes, has captured the imagination for decades. Einstein and Rosen once proposed bridges in spacetime, now called Einstein-Rosen bridges, which are essentially non-traversable wormholes hidden inside Schwarzschild black holes. But again, these require idealized conditions and likely collapse instantly if any matter tries to pass through. So while it's fun to imagine black holes as cosmic portals, the evidence suggests they're more like cosmic dead ends. Let's now turn to quantum mechanics and the role it plays near black holes. Even though your fall is governed mostly by gravity, quantum effects become crucial when we consider the fate of information. As mentioned earlier, the black hole information paradox arises because general relativity says information is lost in a black hole, while quantum mechanics says it must be preserved. In 1974, Stephen Hawking showed that black holes aren't completely black. Due to quantum fluctuations near the event horizon, they emit radiation, now called Hawking radiation. Here, how it works. In empty space, virtual particle-antiparticle pairs constantly appear and annihilate each other. Near the horizon, one particle might fall in while the other escapes. To conserve energy, the escaping particle must have positive energy, so the infalling one has negative energy, reducing the black hole's mass. Over immense timescales, the black hole evaporates. The temperature of this radiation is inversely proportional to the black hole's mass. The formula is Hawking temperature equals Planck's constant times the speed of light cubed divided by 8 times pi times the gravitational constant times Boltzmann's constant times the mass of the black hole. Written out, T equals h times c cubed divided by 8 times pi times g times k times m. For a solar mass black hole, this temperature is about 60 nanokelvins, far colder than the cosmic microwave background, so it absorbs more energy than it emits. Only when the universe cools further will such black holes begin to evaporate. But for a tiny black hole, say, the mass of a mountain, the temperature could be billions of degrees, causing it to explode in a burst of high-energy particles. Now here's the problem. Hawking radiation appears to be purely thermal, meaning it carries no information about what fell in. If the black hole evaporates completely, the information seems lost forever, violating quantum unitarity. This contradiction has led to decades of debate. One resolution comes from the holographic principle, inspired by string theory. It suggests that all the information contained within a volume of space, including everything that fell into a black hole, is encoded on its boundary, the event horizon. The horizon acts like a hologram, storing three-dimensional information on a two-dimensional surface. When Hawking radiation is emitted, it subtly encodes this information, preserving it even as the black hole shrinks. In 2019, physicists made progress using the concept of quantum extremal surfaces and islands in the gravitational path integral. These calculations suggest that information does leak out, but only after the black hole has evaporated halfway, what's called the page time. Before that, the radiation appears random. After, it becomes correlated with earlier emissions, revealing the hidden information. But again, none of this matters to you as you fall in. Hawking radiation is far too weak to detect. Your personal timeline ends long before evaporation begins. Let's also address a subtle point about perception. As you fall toward the singularity, do you see the entire future of the universe flash before your eyes? Popular science often claims this, but it's misleading. While gravitational time dilation means that, in principle, you could receive light signals from the external universe that were emitted over billions of years, the reality is more constrained. First, the light has to catch up to you as you're accelerating inward. Second, the blue shift becomes extreme, turning visible light into gamma rays, which would fry you long before you could see anything. Third, the window of opportunity is tiny. For a stellar mass black hole, you have microseconds inside the horizon, for a supermassive one may be hours. In that time, you might receive signals from a finite, though possibly large, chunk of the universe's future, but not all of it. And crucially, you can't interact with that future. You're causally disconnected from it once you're inside. So no, you don't witness the end of time. You witness darkness, distortion, and disintegration. Now let's talk about what an outside observer sees, not just in terms of light, but in terms of physics. From their perspective, you never cross the event horizon. Instead, you appear to slow down asymptotically, your image freezing just outside. This isn't an optical illusion. It's built into the coordinate system used by distant observers. In Schwarzschild coordinates, the time coordinate diverges at the horizon. But this raises a paradox. If you never cross the horizon from the outside view, and you do cross it from your own view, which one is real? The answer is that both are valid descriptions within their own reference frames. General relativity doesn't privilege any single observer. Reality is relational. There is no universal clock ticking in the background. Time is local. This leads to the concept of complementarity in black hole physics, proposed by Leonard Susskind. It suggests that the experiences of the infalling observer and the distant observer are both correct, but they cannot be compared directly, because no single observer can access both descriptions simultaneously. It's like wave-particle duality in quantum mechanics. Light behaves as a wave or a particle depending on how you measure it, but never both at once. Similarly, the black hole interior and the exterior description are complementary views of the same reality. This idea helps resolve the firewall paradox. If complementarity holds, then there's no contradiction between a smooth horizon, for the infaller, and information being encoded on the horizon, for the outsider. The two descriptions simply apply to different observers and can't be combined into a single global picture. But not everyone agrees. Some argue that recent developments in gravitational path integrals and replica wormholes suggest that the interior might not exist as an independent region at all, that it's emergent from the quantum entanglement of the Hawking radiation. In this view, the singularity and the interior are not fundamental, but approximate descriptions valid only for short times. This is cutting-edge theoretical physics, and the debate is ongoing. What's clear is that black holes force us to rethink what space, time, and information really are. Let's now consider observational evidence. We can't see black holes directly, but we can observe their effects. Stars orbit invisible massive objects at the centers of galaxies, like S2 star orbiting Sagittarius A at the Milky Way's core. Gas falling into black holes heats up and emits X-rays, which we detect with space telescopes. Gravitational waves from merging black holes have been observed by LIGO and Virgo, confirming predictions of general relativity with stunning precision. And in 2019, the Event Horizon Telescope captured the first image of a black hole's shadow, the silhouette of the event horizon against glowing accretion disk in the galaxy M87. The bright ring is light bent by gravity, and the dark center is the photon sphere and event horizon. This image matched simulations based on general relativity almost perfectly, giving us confidence that our understanding of black hole geometry is correct, at least outside the horizon. But inside, that remains hidden. By definition, no signal from beyond the event horizon can reach us. So all discussions of the interior are theoretical, based on extrapolating known laws into unknown regimes. Still, thought experiments about falling into black holes have driven profound advances in physics. They've led to insights about entropy, thermodynamics, quantum information, and the nature of spacetime itself. In fact, black holes have entropy, proportional to the area of their event horizon, not their volume. The formula is entropy equals Boltzmann's constant times the area of the event horizon divided by 4 times the Planck length squared. Written out, S equals k times a divided by 4 times L sub p squared. This hints that spacetime might be emergent from more fundamental quantum degrees of freedom, much like temperature emerges from the motion of atoms. If true, then the smooth geometry of general relativity is just an approximation, a coarse-grained view of a deeper, discrete reality. Returning to your fall, as you approach the singularity, spacetime curvature becomes so extreme that quantum gravity effects dominate. Distances lose meaning. Causality breaks down. Concepts like before and after may no longer apply. Some theories suggest that time itself dissolves into a quantum foam, where topology fluctuates wildly. In such a regime, asking what happens next may be as meaningless as asking what's north of the North Pole. The question assumes a structure that no longer exists. But let's not end on total uncertainty. Even if we don't know the final moments, we do know the broad strokes. You fall in, you're stretched and squeezed. You hit a region where known physics fails, and your world line, the path you trace through spacetime, ends. Yet in a strange way, you live on. Your mass, charge, and angular momentum are added to the black hole. Your information, if the holographic principle is correct, is encoded on the horizon. And over eons, as the black hole evaporates, that information may be returned to the universe, scrambled but preserved. So your journey isn't just destruction, it's transformation. And in physics, transformation is the closest thing we have to immortality. Now, let's tie everything together. The key lessons from falling into a black hole are: first, gravity is not a force, it's the curvature of spacetime. Massive objects warp the fabric of the universe, and what we perceive as gravitational attraction is simply objects following straight paths in curved geometry. Second, the event horizon is a one-way membrane in spacetime. It's not a physical barrier, but a causal boundary. Once crossed, no communication with the outside is possible. Third, tidal forces arise from differences in gravitational pull across space. They depend on the black hole's mass and your distance from the center. Small black holes kill you early, large ones give you a brief reprieve. Fourth, inside the horizon, space and time swap roles. The singularity is not a place you go to, it's a moment you arrive at, and it's unavoidable. Fifth, our current laws of physics break down at the singularity. To understand it, we need a theory that unifies general relativity and quantum mechanics, a goal that has eluded physicists for nearly a century. Sixth, black holes are not just destructive. They're thermodynamic objects with temperature, entropy, and the ability to radiate. They obey laws analogous to the laws of thermodynamics, suggesting deep connections between gravity, quantum theory, and information. Seventh, observation and theory together confirm that black holes exist and behave largely as Einstein predicted. But the interior remains one of the greatest mysteries in science. As you listen to this, whether awake or drifting off to sleep, remember that black holes aren't just out there in distant galaxies. They're in here, in our minds, pushing the limits of human understanding. They remind us that the universe is under no obligation to make sense to us, and yet, through reason, math, and observation, we keep chipping away at the unknown. So the next time you look up at the night sky, imagine the silent giants lurking in the dark, warped regions of spacetime where time ends, light vanishes, and physics stands on the edge of revelation. And know that by contemplating them, you're participating in one of humanity's oldest and noblest quests, to understand our place in the cosmos. Thank you for joining this journey. May your dreams be filled with curved spacetime, gentle tidal forces, and the quiet hum of the universe unfolding. Good night, sleep well, and may your dreams carry you gently through the curves of spacetime, far from singularities, safe within the quiet glow of distant stars.